We're going for polar areas today, part one. So first off, we're going to find the intersection of two polar graphs. So we're going to find the intersection of two graphs that are r is equal to 1 minus 2 cosine theta and r is equal to 1. So let's go ahead and graph r is equal to 1 first. I'm going to plug in angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi to make one full rotation. So when I plug in 0, there is no theta, so that would be a radius of 1 all the time. So this is a circle. So if I go ahead and graph this at angle 0, I'm going to plot the point 0 at angle pi, or pi over 2, or I have a radius of 1, pi over 2, a positive radius of 1, 3 pi over 2, a positive radius of 1. So I end up with a circle. Okay. And for 1 minus 2 cosine theta, this is a limosome. My a is 1, and the absolute value of b is 2. So that means that the a over b is less than 1, which is going to give me an inner loop. Okay, so we're going to start with 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. So the cosine of 0 is 1, so I end up with 1 minus 2, which is negative 1. And then the cosine of pi over 2 is 0, so 1 minus 0 equals 1. Cosine of pi is negative 1, so I end up with 1 plus 2, which is 3. And then the cosine of 3 pi over 2 is also 0, so 1 minus 0 is 1. And then cosine of 2 pi is positive 1, so the 1 minus 2 is negative 1. So I graph these at 0. I'm going to go backwards 1 unit. And then at an angle of pi over 2, I go up 1 unit. An angle of pi, I'm going to go to the left 3 units, 1, 2, 3. And then 3 pi over 2, down 1 unit. And then I'm just going to sketch this in. Okay. One thing I like to note is where each one of my curves starts with, where the curve starts at theta equals 0. So for the inner loop, theta is equal to 0 gives me a radius of negative 1. So it was this first point, the top point on the inner loop, or the leftmost point on the inner loop, I guess. That gives me my starting. This is the start of r is equal to 1 minus 2 cosine theta. Okay. And then it moves in the counterclockwise direction. So it's going to go this way. So it loops around and then loops back towards the inner loop point. Okay. For the circle, we start at 0, 1. So we actually start at this point 0, 1 right here. So, okay, so I can see right now there are 3 points of intersection. So when I solve for my points of intersection, I'm going to make sure I have 3 points. We need to set the two equations equal to each other. So I have 1 minus 2 cosine theta is equal to 1. Subtract 1. Negative 2 cosine theta is equal to 0. Divide by negative 2. So I have cosine of theta is equal to 0. So cosine theta is equal to 0 when cosine is pi over 2. And then at 3 pi over 2, or you could have written that as pi over 2 plus pi n, because the angles are exactly 180 degrees away from each other. Okay, so I'm going to stick with this for now. So I have the 2 points of r comma theta at pi over 2. The radius is 1. I'm going to use the circle equation because that seems like a lot easier to me. Okay. And I'm going to get 3 pi over 2 comma and 1 as the radius. Okay, but wait a second. That's only 2 points of intersection. I know there's a third point of intersection from my graph. What about this guy right here? So from the graph, I'm going to write it over here. From the graph, I can see that the point negative, it's this one right here, this one, that the point -1, 0 is on the graph of r is equal to 1 minus 2 cosine of theta. And then on the circle, the point pi comma 1, or 1 comma pi, sorry, I said that backwards, comes from the equation r is equal to 1. Remember, so what happens here is that on the graph, the points cross the same location, but not at the same time. So we remember in polar coordinates that there's a lot of different ways to write the same location. So we have to remember to look for like co-terminal points, basically. So what we're saying is that these 2 points will not collide with one another. They will not intersect each other at the same time. One of the points will cross the point -1, 0, and then later the circle will come and cross the same location, but using the ordered pair 1, pi. So the third order pair is -1, 0, or you can say 1, pi, either, because they're essentially interchangeable. Okay. All right. So we're going to find the next part is to find the area under a polar curve. We do that by taking the integral, 1/2 of the integral from a to b of r squared times d theta. We're going to start with r is equal to 2 plus 2 sine theta. So I use my detective skills to figure out that this is a cardioid since a is equal to 2 and the stretch is also equal to 2, so 2 over 2 is equal to 1, which gives me a cardioid. So I'm just going to go ahead and plug in my angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, I'm going to sub those into r is equal to 2 plus 2 sine theta. So when sine 0 is equal to 0, so we end up with 2 plus 0, which is 2. Okay, and then sine of pi over 2 is +1, so I end up with 2 plus 2, which is 4. Sine pi is 0, so I end up with 2. Sine 3 pi over 2 is -1, so 2 minus 2 is 0. And then back to 2 pi, I end up with 2. I'm going to go ahead and sketch this in. I start with 0, 2, so facing angle 0, I graph out 2 units to the right. And then at pi over 2, so going upwards, I need to graph a positive radius of 4. And facing pi, a positive radius of 2. 3 pi over 2 is 0, so it's going to be at the pole. It's a little sharp, but that's okay. Okay, that's fine. Okay, so when we're talking about the area under the curve of a polar graph, we're taking the length from the pole to the curve. So we're adding up the lengths from the pole to the edge of the curve. Okay. So we're we're going to take an infinite number of these lengths and add them all up together. Okay, that would be 0, and then we move back. And I know that right here at pi at 0, the radius is 2. So this is 2, 0. So that's where we're starting our curve. The last angle that we're substituting in is 2 pi. So my bounds are going to be from 0 to 2 pi. So to get my area, I'm just going to take 1/2 times the integral from 0 to 2 pi of r squared. R is the equation. So I'm going to do 2 plus 2 sine theta, all squared, d theta. And then I take out my handy dandy calculator and I get area is equal to 18.849 or rounded 18.850, which I also know is equal to 6 pi. Okay? So I just took the value I got from my calculator and divided it by pi, and I got 6 pi, or 6. So I know 18.849 is equal to 6 pi. Okay, let's go ahead and do another one. So we're going to find the area of one petal of 2 sine 3 theta. I know that this equation, 2 times sine of b theta is going to, or d theta, value times theta is going to give me rows. And since it's odd, since the multiplier, the horizontal stretch factor is odd, we're going to get 3 petals. And I have the 2, which gives me the vertical stretch value, which gives me a radius of 2. Okay, so what I do is I find the zeros. So I'm going to set my equation equal to 0. 0 is equal to 2 sine 3 theta, divide by 2, giving us 0 is equal to sine 3 theta. Okay, and then I'm going to take the inverse. So I get sine 3 theta is equal to sine of an angle is 0 when sine is 0 plus or pi. So I'm going to put pi n. Remember, it's like when it's 0 or when it's pi, and that's nice because these are 180 degrees from each other. Doesn't always happen in sine, but in this case it does. Okay, so I get 3 theta is equal to 0 plus pi n. Divide by 3. I get theta is equal to 0 plus pi over 3 n. So I'm just going to make a list of my zeros, which are 0, pi over 3, 2 pi over 3, 3 pi over 3, and then after that, since there's 3 petals, we really have 3 zeros. But remember, what happens with a rose curve that has an odd multiplier in front of theta is that the graph repeats itself. So it traces itself around the second rotation. So I only need this many zeros. So my max values are in between the zeros, and that's when r is equal to 2. So in between 0 and pi over 3 would be pi over 6. And then in between pi over 3 and 2 pi over 3 would be 3 pi over 6. And then 5 pi over 6. And I know this is equal to pi over 2, but I like to write it like 3 pi over 6 because it makes sense in my head. Okay, so I'm going to go ahead and graph this. I'm going to start with at pi over 6, I have a 0. And at pi over 2, I'm going to have a 0. And at 5 pi over 6, I'm going to have a 0. Oops, I did that wrong. Ooh. Pause. All right, I thought I made a mistake, but I'm okay. So I have, just to verify, I went ahead and made a little table of theta and r. So at pi over 6, I get 2, r is equal to 2 times the sine of 3 theta. So I get r is equal to 2 times the sine of 3 times pi over 6. So that's equal to 2 sine of pi over 2. Pi over 2 is 1, so we end up with a radius of 2 at pi over 6. So that gives me, at this pi over 6, I have a radius of 2. 1, 2. Okay. And then at where I think I have another max at pi over 2, I'm going to do 2 times the sine of 3 times pi over 2, which is 3 pi over 2, which gives me a negative 1. So I end up with negative 2 as my radius. So the ordered pair, I'm going to end up moving down 2 units at pi over 2. So this is negative 2 comma pi over 2. And then our third max will happen at 5 pi over 6. So we're going to do 2 times the sine of 3 times 5 pi over 6. Okay, the 3 cancels to give me 2 sine of 5 pi over 2, which is equivalent to 2 times the sine of pi over 2, because I subtracted out 1 full rotation, or 4 pi over 2. So I end up with a radius of 2. So at 5 pi over 6, which is right here, almost 30 degrees to the negative x-axis. It's not quite. Let's see if we can do a little better. Okay, we end up with the point positive 2 comma 5 pi over 6. All right, so now what happens is the graph starts at 0, 0 at the pole, because that's where my 0 is, and then I move out to pi to 2 comma pi over 6, back to the pole, and then down to negative 2 comma pi over 2, back to the pole, then out to the max radius at 5 pi over 6, and then back to the pole. And what I need to get is the area of one of these petals. So I'm just going to get the area of this first quadrant petal. I know it starts, we start at theta is equal to 0, and the petal ends at when it goes back to the pole at pi over 3. So the area that we're looking at is from the pole to the curve, like adding up all the little lengths from the pole to the edge of the curve around this one little petal here. Okay, so to get our area, we do the area is equal to 1/2 times the integral from 0 to pi over 3 of 2 sine 3 theta, or r, squared d theta. And I'm going to substitute that into my calculator. Ooh, looking for my calculator. Okay, so I have, what I did was, you don't have to, but I changed my calculator into polar mode. Okay, so right here into polar mode. And I actually went ahead and graphed the equation 2 sine 3 theta for r. and it looks like this, and I just verified that it matched my graph. You can use the table function. So I thought I made a mistake, but I was like, okay, I'm going to double check that pi over 6 is equal to the radius of 2. And then pi over 2, I just wanted to double check that equals to the radius of -2 to make sure I graphed in the right direction. Okay, so you can use the table function like normal. And then I am going to go ahead and fill in my integral. So I have 1/2, which I'm going to type in as 0.5, times the integral from 0 to pi over 3 of 2. I'm actually going to put in a second set of parentheses here. So 2 sine 3 theta, or 3 theta. If you're not in polar mode, if you're in rectangular mode, you use x, and if you're in polar mode, you use theta, you'll come out with the same answer, okay? And then close my parentheses for the angle. I'm going to close my parentheses for the equation, square that business, and then make sure I take the integral with respect to theta. So I get 1 point, the area is equal to 1.047. And just to check to see if it's like a nice multiple of pi, I'm going to divide by pi. And I get, oh, it's 1/3. So I end up with area is equal to 1.047, which is equal to pi over 3, because it's 1/3 times pi. All right, last one. We're going to find the area of one petal of r is equal to 4 cosine 2 theta. This is again a rose, but when we have an even horizontal multiplier, we end up with double the petals, so 4 petals. And then my vertical stretch is 4, so a radius of 4. All right, or max radius of 4. So I'm going to start with my zeros. Honestly, cosine graphs are a lot easier because our zeros are our max radius. Okay. Sorry, our max radius starts at theta is equal to 0. So finding my zeros, I'm going to set 0 equal to r, which is 4 cosine 2 theta. Divide by 4 to give me 0 is equal to the cosine of 2 theta. So 2 theta, cosine of theta is equal to 0 when cosine is pi over 2. And 0 is one of these that, since the angles are 180 degrees away from each other, I can just write plus pi n. Okay, then to get theta by itself, I'm going to divide by 2, give me pi over 4 plus pi over 2n. Okay, so I'm going to have a 0 at theta is equal to pi over 4, add 2 pi, or pi over 2, which is 3 pi over 4, 5 pi over 4, and 7 pi over 4. Continues on, okay? And then we have the max values of a rose are halfway in between those values, in between these thetas. So I am going to actually extend out my angle to be negative pi over 4, then pi over 4, so that I can see that my max value is halfway between, which is 0. Halfway between would be 2 pi over 4, and then 4 pi over 4, then 6 pi over 4. And I know those reduce, so we can do theta is equal to 0, pi over 2, pi, 3 pi over 2. Okay, so when I graph this, it's going to be like a rose, because we said so before. And at 0, I'm going to have a max radius of 4. At pi over 2, I'm going to have a max radius of 4. At pi, I have a max radius of 4. And 3 pi over 2, I have a max radius of 4. Next up is to graph in the petals. So I'm going to start here. Boom. Okay, they don't quite go in this direction, but that's okay. Okay. So the graph actually starts with the ordered pair of 4, comma 0. R is 4, radius is 0, theta is 0. And then what happens is it swoops back to the pole, okay? And then it swoops around this way, okay? We can graph it and see, but we don't really need to today. So to get the area, I just need the area of one petal. So I just honestly just need to get, you choose the bounds to be from 1, 0 to the next. So I'm just gonna go ahead and look at my zeros and be like, well, the first 0 was at pi over 4, and then the second 0 is gonna be 3 pi over 4. But you could also choose any of these 2 consecutive zeros to get to be the bounds for your area. Okay, but I'm going to choose the first 2. So I have the integral from 1/2 of pi over 4 to 3 pi over 4 times r, which is 4 times the cosine of 2 theta squared d theta. I'm going to type this into my calculator. I'm going to use this one to help. Nah, I'm going to make. Okay, so I'm going to do 0.5 times the integral of pi over 4 to 3 pi over 4. I like to add a set of parentheses. And we have 4 times the cosine of 2 theta. Close for the angle, close for the equation, square that, and then take the integral with respect to theta. And I got 6.283. This should be recognizable. 283. Divide this number by pi to see if pi goes in evenly. And we get 2. So 6.283 is equal to 2 pi. All right, so that is our first go about, and tomorrow we're going to look at some more polar areas. Bye.